Excellent. So again, my name is Gill. I'm with Sentek Technologies. We're going to go over a few topics in regards to soil monitoring and monitoring for moisture, temperature, and salinity, which is Sentek's core business. Just to bring in the reality of today's gloom and doom in regards to water scarcity, we're all heard probably 20 times that there's this upcoming demand and populational demand and more weather variability, right? And just so we kind of focus back on what Canada is in regards to Canada being a net exporter of water, right? What they call virtual water exports through crops, through animal products, and so forth. And the seasonal variability of water availability in Canada is also starting to become quite visible on a global scenario, where you can see here in the southwestern area of Canada, which coincides with parts of the Great Plains of the U.S. in regards to water scarcity. And then as you see the global demand of net importers of virtual water here on the bottom right. And by the way, anybody can interrupt me anytime if you have any questions. I'll be more than glad to answer. And then just moving forward, I think as growers become more and more aware of what the variables come within each season, it seems like that the trend is you plant the earliest and you harvest the earliest, and that minimizes your exposure to environmental risks or weather risks, right? So we're just looking at some acreage in regards to wheat, canola, barley, by far the world's largest lentil producer, and a few other crops. And within that scenario of where the crops are grown, the row crops are grown on dryland farming here in Canada, you can also see that the seasonal variability of water availability and soil moisture can also be pretty dynamic, where understanding what you have stored in the ground and also with temperature allow you to make better decisions. And we can see from previous research that there's always a penalty, right, in regards to tons per hectare, bushels per acre, in regards to planting dates. So the question that we need to ask ourselves, what is the total yield left behind from planting decisions from lack of real-time data, right? So if you go one slide back and you look at your planting dates and then see where that fits. This is a publication came from University of Nebraska. And I'm pretty sure that Canada has probably better data because you guys have a much harsher climate in regards to yield loss and so forth. And then just moving forward. So Sentek was founded in 1991 by Peter Buss. It was founded by a group of 50 onion farmers in South Australia. That's where our headquarters is. We're based in Adelaide, Australia. And he was inquired by a group of farmers in regards to what solutions he could bring in regards to water availability and monitoring salinity. And there was another co-founder of the company that came from the aerospatial engineering industry, and they decided that capacitance was the correct technology, right? And just a simple explanation of what capacitance is, it's basically converting a voltage into a frequency, and the travel of the frequency through the soil media is how you're able to capture water content as well as temperature and salinity. So this is the initial prototype on how the probes were developed. And then what is the value of real-time soil monitoring, right? Different growers, different farmers, different operations will always have different end goals, but I try to summarize everything that could be of value in regards to data to a farmer, right? So if the ground is irrigated, when does the irrigation need to happen based on soil moisture profile, right, without causing plant stress? As a fact, plant stress, for example, in California, we work a lot with almonds, right? So if almonds has a trigger effect of closing down the stomata, it takes on average about 2 weeks to recover from that initial abscisic acid release of stomata and water stress. So that's where it costs you yield if the plant ever goes into shutdown mode. How long to irrigate without wasting water, energy, and fertilizer? This is the objective, to keep water within the root zone of any given crop. Field irrigation urgency. If you have a limited supply of water, which fields need to be addressed earlier based on water that is stored within the root zone. From the sensors, we can also determine what is field capacity from the site right? That's a very subjective parameter to be looked into given field practices, tillage practices, organic matter, and so forth. And also, what is the onset of stress? Our software now has a machine learning feature which allows for the prediction on the next irrigation event, how to keep the fertilizers in the root zone. Because the soils are stacked in a profile format, you are able to determine if you would be leaching fertilizers past the root zone, how much water to apply in leaching irrigation if you have salts that are damaging your crops. Root zone development, because the probes are also again in a profile format, you can detect based on sensor depth where is water being extracted from. Number of stress days from either from waterlogging or drought. In many instances, this has been used as crop insurance data. Infiltration rates based that determines your irrigation run times, right? So the infiltration rate, which is hydraulic conductivity, basically guides how long you should have your irrigation on. If you're growing vegetables, for example, maybe a short run time is adequate. And then if you're growing grapes for wine or walnuts, those run times can be much longer, up to 48 hours, for example. Drainage losses, how much water have you lost below the root zone? Soil salinity changes as a trend. Soil temperature. We're really going to explore this feature given the amount of what we call dryland farming that happens in your region, and how critical planting dates are based on soil temperature. Irrigation and rainfall effectiveness. Sometimes if you have access to irrigation, you say, oh, I got it, a rain, I don't need a water. Was that enough to fill your root zone? And why does Sentek differentiate itself from other players in the segment? We have an undisturbed installation method that the soil moisture is immediately valid. You don't have to wait for any normalizing or any equalization with the adjacent soil. As soon as you put the probe in the ground, the data is valid. The accuracy of the data, because we provide the capacitance probe in the mark with the highest frequency, the durability of our probes, and the quality of our products. And then just moving forward, here are a few examples of the solutions that we have. The probes are always designed to meet the profile of the root zone. So for example, if I'm growing, like you said, a vegetable, I probably have a 30 centimeters or maybe a 60 centimeter probe. Whereas if I'm working with a tree crop or even alfalfa, right, I'd be monitoring all the way down to 150 centimeters. And the soil probes measure volumetric water as percent, salinity as what we call volumetric ion content. And all the probes will have a temperature sensor every 4 inches or every 10 centimeters along the soil profile. And how do we get that data from the probes? It's through two options in regards to telemetry. You either can have a cellular automatic uploads. You can have data coming from the cloud automatically every 15 minutes, every 30 minutes, every hour. Or we also have a new technology which is operated by a smartphone app, which is a Bluetooth probe, and it contains a logger, and it continuously logs the data. And then you physically go to the field and you upload that data to the cloud with your smartphone and an app. And then we have the software, how you visualize and make decisions from the data collected from the soil moisture probes. And also we offer open integration options, right? We can either give you API into your software, we can provide SDI-12 probes and or Modbus probes into any platform. And we are sold globally through a network of distributors. We have a few distributors that we have in Canada. And then here's an example in regards to a unit that has a 4G modem installed in the field. It's called the Compact. And to the left, we have the soil moisture probe called the Drill and Drop. And then to the right, we have the visualizing software, which is Irrimax Live. And then the probes can come into 30 centimeters, 60, 90, 120. And now we just recently launched a 150 centimeter probe. And the unique installation process of our probes is what makes a huge difference in regards to data quality. The probes are all tapered to have a carrot format where you use an auger, right, to drill a hole that's the exact diameter of a probe, and you slide the probe as in these pictures on the bottom right. And then you just have a nice contact between the probe and the adjacent soil. And here's an example of the Bluetooth probe. This is very practical. I would say a lot of the times for dryland farming and vegetable growers that are in close contact with the field frequently. And the probe will continuously log the data, right? And all it needs is a AA battery and a smartphone app. And then why undisturbed installation? So when you disturb the adjacent soil, you automatically alter the water holding capacity of the adjacent soil, where you also create a condition, what we call preferential flow. And many times that's not the representative water holding capacity of the most part of your field. So that's why we really emphasize that the probes need to be installed in an undisturbed format. And then that's why we developed this system where you have a tapered auger that matches the exact diameter of the probe. And on the far right here, we have a tripod to keep that probe installed vertically. And then consideration in deploying a probe, right? So the first thing you need to look at in regards to your field that you'll be managing is, do I have a similar soil texture for my management zone, right? So soil texture is the baseline of any irrigation and soil management, because that really guides water holding capacity, your fertility program, and so forth. In regards to the root zone, the probe should be installed adjacent to the root zone in regards to the most representative water extraction sphere of what we call the sphere of influence. And then again, the installation method is pretty straightforward in regards to using a tapered auger and so forth. And then why is soil temperature so important for planting decisions? I just got this example off the champion in regards to corn yield in the U.S. And in his article, he really emphasized, I actually quoted from an article that he wrote, that the soil temperature has to be 56 degrees or 13.3 Celsius from 7 to 8 days, right? So that's what his guideline is to achieve, to be the champion in corn yields and soybeans in many instances also. And below here, I just added a table in regards to what are the average temperature planting thresholds for different crops. I know that you can see that a bit higher ones would be millet, sunflower. You guys grow a lot of sunflowers up there and so forth. Even soybeans is a little bit higher than average. And then here is the link on where you can access this information. And then for a farmer, time is yield, and real-time soil profile temperature and moisture are critical to make planting decisions, right? Just going back to what does it cost the entire industry per se, this planting decision making between each individual farmer, right? So that's a parameter that a lot of the guys don't put their numbers on a piece of paper. How much does it cost them if they miss a few days? Because that's where the penalty comes, right? You can lose an eighth to a fourth, up to 5/8 bushels per acre per day that you're not planted based on optimum growing conditions. Here we have an example of, actually, this is on my farm. I have a little farm, and I just wanted to show you my annual annual temperatures for the soil here. I actually turned it over to Celsius. So the lowest Celsius I can get is on the top 4 centimeters of the soil, which my lowest temperature was 9 degrees. And my highest temperature at that 4 centimeters deep was 29.99 Celsius. So that's basically the amplitude of variability that I have in soil temperature from the lowest temperature to the highest. And going back to what we were talking about, having those consistent 7 days above 56 or 13 Celsius would be the trigger for corn, for example, on having the most favorable conditions for planting. So that's where real-time monitoring really brings this data to light on when to pull the trigger as a decision-making factor that For larger operations can mean a lot. And then we're just going to go back to what are the basics in reading soil moisture data. Saturation, you have no open pore space. Field capacity, you have the perfect amount of water and adhesion between soil particles and water. And wilting point is when the matrix potential is higher than the plants can actually extract from it, right? And then we have the plant available water, right? And you could be either on the top end where you can have a logged situation, waterlogged situation, and at the very bottom, you can have a water stress crop. And understanding your soil texture is critical because, like we mentioned, the particle size distribution for any given soil is what allows to determine what the water holding capacity is, and then field capacity, and then wilting point, and then plant available water. So a well-structured clay, a permanent wilting point is at about 30% volumetric water content, whereas in a loam, you're not too far from that, but that would be field capacity. So you could see that in a close number, one plant could be dead and one plant could be in perfect good conditions. So that's where understanding your texture critical for good yields. Here, we're going to explore what we call the maximum allowed depletion based on different crops, right? And we just like to emphasize what could be the differences, right? I'm a beer drinker, so I really like hops. So hops potentially could be a pretty drought-resistant crop, right? You can let water availability based on any kind of soil type drop down 50%, whereas potatoes, you can only drive that down to 35%. Right? Anything past 35% from field capacity reduction will start to cut into your yields, right? And between those two, you can separate plants into what we call isohydric plants, right? Where they immediately close their stomata when water becomes scarce to limit evapotranspiration, right? And then you can see that potatoes actually respond pretty well into shutting down their stomata, even though the threshold is pretty low. But they're aware of it and they close down pretty fast, right? Beans, potatoes, sweet potatoes. And then anisohydric plants, they keep their stomata as open as long as possible to maximize carbon uptake and photosynthesis, even when it's starting to reduce, when the plant sees a reduction in water availability. And these are some plants that will still try to grow under restricted water availability: apples, cowpeas, corn, and peas. So this is how we basically determine how we're going to manage our crop in two major classes of stomata reaction. And actually, there's research based on also number of stomata by electronic microscopes on the surface of any given leaf. And then we're just going to go through a quick exercise in regards to determining field capacity and wilting point by soil texture and water holding capacity. This example here, we're using mint as a crop. We support quite a few growers in the Pacific Northwest here that grow mint, right? And then when you look at the chart here, you can see mint has a maximum allowed depletion of 40%, right? So the quick math that we can do is basically from a lab analysis, you can basically get what is your field capacity and what is your wilting point. And the labs will have different protocols to determine those two. But once you get that from a lab, you can subtract field capacity minus wilting point. That's your total available water. And then you'll multiply your total available water by the maximum allowed depletion, right? And that's going to be your plant available water in percentage. And then all you have to do is basically subtract plant available water from field capacity, and that becomes your onset of stress, or if you have access to irrigation, turn your water on. And in some instances, if this is the threshold for a given crop that's in dry land, you probably would not invest any more in that field in regards to you wouldn't side dress, you wouldn't put any more fertilizers in it, and so forth. And then if you have irrigation, once you've reached field capacity, there's not a reason to keep watering past field capacity. You'll start to leach your fertilizers and so forth. And then once you have these two parameters in our software, you just have to multiply it by the number of sensors, and then that you could see it graphed as full point and refill point on a root zone profile format. We're going to see some examples on graphs from those. And then another example, determination of irrigation thresholds using soil texture while water holding capacity for berries, right? So for example, berries, this is a really good website. This is probably my favorite website. The link is right here from the FAO. And then just going through berries here, berries actually has actually it was done for grapevine, sorry, 45%, it's my mistake here. 45% is how much I want to let my grapes dry out, right? And different growers have different strategies based on this too. I know that after veraison, they really cut back on water availability because they want the cell division to stop and the accumulation of phenolics and anthocyanins continue. But going through the exercise again, we're going to, a different soil type, we're going to subtract field capacity minus wilting point. That's going to give me my total available water. I'm going to multiply my total available water times my maximum allowed depletion, which is here for the wine grapes. And then I'll have my plant available water. And then I'll subtract plant available water minus field capacity to give me my onset of stress. And then again, for our software, we'll multiply field capacity times the number of sensors to give me my full point. And then on the bottom end, to when I trigger an irrigation, onset of stress times the number of sensors to get my real fill point. And then here is basically the interface that our software provides. You can see that the top graph will have 1, 2, 3, 4, 5, 6 sensors. The sensors are spaced out 10 centimeters one from the other. So for example, the top sensor is 2 centimeters and then 12 and so forth. And then these circles, the circular areas, are basically water extraction from the roots, right? So that's how we can see where are the roots actually extracting water from. The blue vertical location here is basically showing an irrigation or rainfall event. And you can see that on this stacked graph, all the sensors responded, right? And given the change in amplitude of this water increase, we have an algorithm in our machine learning software that tells me I went past the root zone. So that's why it shows me as a blue overwatered event. Whereas the following irrigation event, I probably didn't run it as long. And then I have a nice green profile to match my root zone. And then based on graph trends, our software can determine when is your next irrigation happening, right? So for example, from where I was at this point here, my next, I was actually saturated for a few days or for a day. And then I was gonna reach field capacity in 17 hours. And then I would really have to water within 35 hours, right? On the bottom right-hand side here, you can see that I would hit my onset of stress in 35 hours, right? So that's a very interesting tool for managers nowadays to know based on what the weather trend was for the past week, where they will be next week in regards to stored water in the soil and crop water usage on any given cycle. And then the next slide here, just really wanted to emphasize where the algorithm of our software shows if I watered perfectly, where all my greens are perfect irrigation events. And you can see that on this event here, I have a red line on it because I irrigated and I probably had to do something. I don't have a full automated system. So I only watered the top 3 sensors and my bottom 3 sensors never got a response from soil moisture. And that's why you see that there's no response from the deeper probes or deeper sensors. And that's why we have that red mark on my irrigation analysis. And I'd like to emphasize the bottom graph where you have the blue and the onset of stress. The green line between green and blue, that's where my field capacity would be. And my onset of stress would be the math we did. This happens to be a field that has plums. So I grow black plums. So I have a crop coefficient, I think of, not a crop coefficient, I have a maximum allowed depletion of 40%. And then every spike is an irrigation event, right? So I can let the water dry out or the plant evapotranspirate this water as it uptakes carbon, and then I'll irrigate again and again throughout the season. The next slide really shows water is only really used by crops during daytime. 95% of water usage on plants is to keep the leaves at a temperature that photosynthesis can happen. 5% metabolic uses. So then you can really see that the majority of water is used for thermal regulation on a leaf surface parameter. And then you can see that some days you'll have more water usage when it's hot and other days when it's not. And then the nighttime, there's literally very little water usage. And then if I overwater, you can see that I'm way above field capacity and the water is going to continue to drain until I reach field capacity. This event here really shows that there's no real growth, right? If you really saturate a field, there's no plant growth, there's no oxygen, there's no real growth. And you can see that it's just flatlined. The trees or the plants can't use any water because it's so saturated. And after a while, you'll start to see some dynamic movement between evapotranspiration in night times, right? And the same applies that the amplitude is shortened as the plant reduces its power to extract water from the soil, right? And then you can see that it's going to go under water stress from availability. And then again, just showing that you could see the amplitude from water available, and then it shortens its availability. And then you can see that the plants are really going to start to shut down its stomata, stop its growth because there's no water available in the soil. And you can really correlate that with evapotranspiration. This one was really, this was a trial we did with the USDA in regards to determining how important it is to keep an eye on your crops, right? So if you have 15 days or more, either from waterlogging or from water stress, it will cost you 50% of your yield, right? So that's a key factor that a lot of growers that have access to management don't understand, is that, oh, I can get over it, but not really. If you have 15 days or more of stress within the growing season, which is about, let's say 10 to 15% of your row crop growing time, that can cost you 50% of your yield. So if you have access to irrigation or any other management tools, that's really critical to keep an eye on. This slide here, we're just going to emphasize how sometimes rainfall events are not enough to fill the profile if you have access to irrigation, right? So you saw that there was a rainfall here right on the 28th of April. It barely changed the sensor on the first event, right? And the same happened a few weeks later, where only the top sensor really responded at 18% here. And then none of the bottom sensors actually got any water. So not always a rainfall is enough to refill the profile. That's the whole point of seeing the entire root zone and the moisture in a profile format. And then here we had a grower that had a really hard time in regards to managing his pivot. And then we can really track down that he needed to slow down his pivot because based on his passes, it was not enough to really refill that profile. And then as we lowered the speed of the pivot, you can see that we went back into field capacity and then really refilling that root zone profile. And then why is water so important for nutrient uptake? So nitrogen, for example, 99% of nitrogen would only be uptaken if there is available water through mass flow, right? And then the same thing applies to sulfur, 95%. Calcium is a really important one for apples because if you ever see a calcium deficiency in any given crop, you're never really going to be able to address it because it's really uptaken at the time of water uptake. And because it's a structural nutrient, there's no real translocation of the nutrient, right? So that's why having potentially field capacity conditions super important for nutrient uptake. On the left-hand side here, we'd like to show that all plants have the similar pattern in regards to extraction zone. So 40% happens in the top quarter of the root zone profile, and then 30%, 20%, and 1%. So we can really estimate that 90% of all water uptaken by crops will happen within the top meter of the soil. And then our probes really detect where are the roots extracting water from. For example, you can see that the blue line here had very little changes throughout time. And then based on 14th of February, you can start to see the drop in that depth, where if you ever were to water past where the root zone is, you're going to waste water and fertilizer. Here we're showing how we can use the volumetric ion content and fertilizer applications based on salinity in the soil profile, right? So you can see that we have a baseline of volumetric ion content. You apply nitrogen, for example, in this case, and you can see the plants using the nitrogen, where you would make a decision to side dress again once you've gotten down to your baseline as you started the season. And then the question that every single grower has to ask themselves: what is the cost of managing risk in crop production versus return on investment? That's a fine line to walk every day. Here we list the challenges of a modern day farmer. And I really like to see the new Liebig's law adding water and soil conditions and other growth factors to the variables of crop production. In California, water is extremely scarce. Now it's a traded commodity. We can see that the spot market for water now is at $481 per acre foot. So for example, if you're growing almonds in California, you're probably being close to $1,300 an acre every single year if you're buying water in the open market. So that's just to kind of bring some values and economics behind water usage. Whereas in the past, water was just considered just a given commodity by nature, right? But moving forward, you're going to see many industries competing for the same resources. In California, municipalities and agriculture are in the same market to purchase water. So it's changing the dynamics of water usage here. And if you guys have any questions, feel free to reach out. Here is my contact information.
Perfect. Thanks, Gill. We are tight on time now. Can maybe take one really quick question. Otherwise, Gill, if you want to stick around in the session in Feed Loop, perhaps you could answer some directly via the chat as well.
Yes, definitely. I will be present here if anybody has any questions.
Wonderful. Okay, so I guess we will call that. Thank you very much. That was a very interesting presentation. Lots of great information. Enjoy the rest of the day, and hopefully you can join us this evening for the social networking. Thanks, Gill.
Thank you. Thank you, everybody. Bye.